So whenever we talk about energy in a chemical reaction, we're dependent on a fundamental law that dictates how we discuss this subject, and that's the first law of thermodynamics. And the first law of thermodynamics is the law of conservation of energy. This essentially states that energy can change forms, but it is neither created nor destroyed. This is very similar to the law of conservation of mass. We're essentially saying that however much energy we started out with on the reactant side, we have to keep track of all of that energy and account for it on the product side as well. And with energy, keeping track of it is slightly more nebulous compared to keeping track of mass. Sometimes it's fairly easy to keep track of mass in a reaction, but because energy can be given off as heat or as work, sometimes it's a little bit more difficult to keep track of where it is. And so we have a couple more definitions that help us keep track of energy in a reaction. And those are the terms system and surroundings. So the system is where the process itself is actually occurring. And then the surroundings is just anything else around that. Now, there are kind of three different types of systems. There's open, closed, and isolated. So an open system is one where, sort of like an open test tube, where both energy in the form of heat or in the form of work, if something moves, and mass is able to enter and leave the system. So here it's an open test tube, mass can come in, mass can leave, heat can come in or leave. A closed system is one where energy is able to enter or exit the system, perhaps through the form of heat or through the form of work, but mass is not able to exit or enter. And then finally, an isolated system is one where it's just like it says, no mass can enter or exit, and no energy can enter or exit the system. An example here is piston, maybe in a car where there's a combustion reaction occurring inside the chamber. So within this would be an example of a closed system. So no mass or no matter is able to enter or leave the system. It's contained, but energy is able to leave the system either as heat that's given off. So if you were to touch the side of the engine block in your car, that would certainly be hot, or as work that's done by driving the motion in the piston. And so this would be a closed system. The system itself is within this, to be more specific, the system itself is the chemical reaction. And that is what we are going to use going forward. The system is always the chemical reaction. The surroundings is everything else, everything that can absorb heat or give up heat to the system. In the case of this closed system here, the chemical reaction is the actual system. And then the piston itself and the air outside the piston and all of that, that is the surroundings. And that is what can absorb the heat. That is what can absorb the energy in terms of motion. All of that occurs as the surroundings. Okay, so let's make this a little bit more clear. When we talk about energy in a system, we define it really as being just the internal energy. Since our system is a chemical reaction, we talk about the internal energy of a chemical reaction, which is just the sum of all of the component kinetic and potential energies. We're just going to lump it all together and call it the internal energy. Now, a change in energy we always define as being the final energy minus the initial energy. So it's always final minus initial. And we can show a couple examples here where I start out at an initial energy, then a loss in energy where my final state is lower in energy than my initial state, that's always going to be defined as negative because it's final minus initial, and final is lower than the initial. However, if I gain energy, if the system gains energy or consumes it or is given it, then the final state of the system is going to be higher in energy than the initial one, and this will now be positive. A couple of sign conventions here will be helpful. So the changes in internal energy, we can define that as being the sum of the heat that is transferred and the work that is done. So Q is heat and W is work. A couple of sign conventions will be helpful in keeping track of some of these things. So specifically talking about the system, the chemical reaction. For heat, a positive symbol means that the system gained heat, that it was given it by the surroundings. Negative means that the system gave off heat. It gave off heat to the surroundings. Positive for W means that work is done on the system, whereas minus would mean that work is given off, that the system does work on the surroundings in some way. So if we think about chemical reaction, combustion reaction, driving a piston, that would be a case of, this would be a case of negative work. It's work done by the system on the surroundings. And then just for the overall change in energy, if that's positive, it means that the net energy of the system is higher than the initial. And negative means we gave off energy in the process. Okay, a couple more definitions. So whenever heat is added to a system, the internal energy increases. That makes sense. The change in internal energy is Q plus W. So if we add heat, then that's positive heat, and that increases the energy of the system, and then vice versa. Now, there's a couple definitions here. Whenever the change in heat for a reaction is positive, that means that heat is being given to the reaction. That's known as an endothermic reaction. The reaction requires heat, so it sucks heat from the surroundings. Now, endothermic reactions feel cold because your hand, if you hold the vial that has the reaction, your hand is part of the surroundings. The reaction is pulling heat from the surroundings, and so that makes your hand feel cold. An example of this would be this reaction here. If you mix ammonium thiocyanate or thiocyanide here with barium hydroxide, we start out initially at, we have an initial case where we start out at 23 degrees Celsius, and then as we mix them and have a chemical reaction, then heat flows from the surroundings, from the thermocouple into the reaction, and so that causes the thermocouple to cool down, and we have a change in temperature. Because whenever we measure temperature, we're really measuring the temperature of the surroundings, not of the actual chemical reaction itself. Alternatively, if heat is given off in a reaction, that is an exothermic reaction, and it generally feels hot. So any kind of combustion reaction, or here's a violently exothermic reaction. If you take potassium metal and drop it into water, you start out at some energy, and then after you add it, you have a violent reaction where you give off a lot of heat, may actually catch fire, and that clearly is the system giving off heat to the surroundings. The temperature now of the surroundings, which is what we measure, goes up, and we would refer to that as being an exothermic reaction.